There is one example I missed in our last video, and it's an easy example. So I'm going to start a new numbering for examples. So example one of this video is find um, all linear combinations, linear combinations, whoops, of a 1, 3, and in the last video we had 2, 5, but this time I'm going to do 2, 6 instead. So all the linear combinations of 1, 3, and 2, 6. Now, eh, the interesting thing about this is that um, one way we can start figuring this out is by randomly generating some linear combinations and see what happens when we observe the outputs of those linear combinations. So for instance, if we have so some linear combinations are, for instance, 1, 3, let's say 2 of those and maybe 4 of those, 4, 6, and then you end up with 2 and 8 is 10, and 6 and 24 is 30. 10, 30, that kind of looks like 1, 3. Another one could be, I don't know, 5, 1, 3 plus -2. I don't want to do numbers that are too big. So that would be 5 minus 4. Oh, that's going to give us 1. And 15 minus 12 is 3. Boy, that gives us the same one. Oh, that is interesting. Even though we did not add 0, we came back to the same one. How about something like 7, 1, 3, and let's just do 1 of the other one. So that's 7 and 2 is 9, and 21 and 6 is 27. So something to notice is that this is the same thing as 10 times 1, 3. This is 1 times 1, 3. And this is 9 times 1, 3. So it looks like no matter what combination we do, we come back to 1, 3, which means that this is redundant. We don't need 2, 6. It is sufficient to have 1, 3. And actually, we could just use 2, 6 or 1, 3, either one of the two, but 1, 3 is simpler than 2, 6. And consequently, this guy is the one that seems to be more redundant. So when you have two vectors and we ask for a linear combination for the set of all the linear combinations of those two vectors, that doesn't necessarily mean that we're going to generate all of the plane, as we did in one of the examples in the last video when we had 2, 5. So all it took is to twist this a little bit, to change that, to perturb this a little bit, change it from 5 to a 6, and that caused this to not create all of the plane. It creates, this is redundant. We can, since we can create this with a linear combination of that, that means that this is unnecessary for linear combinations. I mean, think about that. If you have A times 1, 3 plus B times 2, 6, well, 2, 6 is really 2 times 1, 3. This is A times 1, 3 plus 2B, 1, 3. So this is really A plus 2B times 1, 3. So that means that all it takes is 1, 3. Whatever we can do with 1, 3 and 2, 6, we can do with simply 1, 3 by changing the number, the two numbers into one number, combining the two numbers. So, so the linear combination, the set of linear combinations of those two vectors is not going to be the plane. It is going to be the same as all the linear combinations of this guy, because this one is redundant. And again, it sounds like a broken record when I say figuring out what vectors are redundant when we are trying to look at all the linear combinations of a set of vectors, is a central thing in linear algebra. Um, very, very central. And again, there's going to be things that are not going to be so central. They're more tangential. They're more they're on their own on the side. But figuring out what is redundant, what is not necessary, is very, very central in linear algebra. And as a matter of fact, in mathematics, it is central to know what is redundant, what is not necessary, what is not essential to a concept or a topic. Okay, let's introduce the dot product. Dot product. If you have two vectors, so example 2, I'm just going to show you with an example. Uh, uh, 2, 7, dotted. So we're going to use this symbol, just a dot, in the middle of the two vectors. And then the two vectors have to be of the same dimension. Otherwise, we cannot perform the dot product. And we may not add vectors of different dimension either. As I have established in the first video, vectors of different dimensions just live in different worlds, and we cannot combine them really. So 2, 7, 5, 9, for instance. And this is going to give us a number. And the way we figure out the number is by multiplying corresponding coordinates. 2 times 5 is 10. Add 7 times 9, which is 63. So the answer is the scalar, the number 73. So the dot product of those two vectors is 73. Yep. Yep. And we always do that. Example 3, even if you have, let's say, a 0 and a negative number. So what we do is 2 times 0, 0, plus 7 times negative 2, negative 14. So the dot product is negative 14, the dot product of those two vectors. So of course, if you multiply with the 0 vector, 2, 7, dotted with 0, 0, we have 2 times 0, 0, 7 times 0, plus 0. So the dot product with the 0 vector is 0. And it is a scalar. Yeah, oftentimes when we multiply things like numbers, you end up with another number, like 2 times 5, you end up with 10, and the three of them are numbers. And sometimes when you multiply things, you don't end up with the same kind of object. So here we're multiplying with the dot product, two vectors, and we do not end up with a vector, we end up with a number. So that is very, very important. If in any kind of an answer you end up with a vector when we are asking for a dot product, you cannot even get partial credit because the answer doesn't even make sense. The answer has to be a regular real number. So what is the relevance of this dot product? There could be more than one, but first let's say you have 2, 7, and we multiply with itself. Yeah, nothing stops us from multiplying with itself. Notice that we end up with 2 times 2, which is 4, plus 7 times 7 is 49, and that is 53. Now, something interesting about this example is that if we compute the length of 2, 7, remember how we did this? We saw that in the last video. Square that, which is going to give us 4. Square that, which is what happens when we multiply with the dot product, plus 49. And we have square root of 53. So indeed, the dot product of a vector with itself is the square of the magnitude or the length of the vector. This is the length of the vector. So there's a relationship, and that will happen every time in any dimension. If you dot the vector with itself, you're going to get a number, which is exactly the square of the length of that vector. Which vector? Well, it doesn't matter because it is the same vector. Or I could tell you this vector, but then you could say, well, What about that vector? Sure, that vector too. 6. Okay, so let me draw a picture first. So 1, 2, 1, 2, 3, 4, 5, 6, 7. So 2, 7 is about there. Uh, and one question we can ask is, what is the, man, I didn't give myself enough room. Let's do it on a new page. So example 6. I'm gonna draw 1, 2, 1, 2, 3, 4, 5, 6, 7. So 2, 7 is about here. All right. How about 2, or rather 7, negative 2? If we go 2, 3, 4, 5, 6, 7, and then negative 2, we're going to be about here. And that's going to give us this. And think about that in the sense, observe this. Yeah. If you start out with 90 degrees and you move in such a way that you move 2 units on the 7, you move 2 units, you end up doing the same kind of motion and you still end up with 90 degrees. So this is what's going on. And what I'm trying to demonstrate is that the two vectors have 90 degrees one from the other. So, and by the way, you also knew that because from basic algebra, since the slope of this line is rise is 7, run 2, and the slope of this line is run of 7, rise of negative 2. So that is negative 2 over 7. And those are opposite reciprocals. And consequently, those two lines are a 90-degree angle. Well, what is the dot product of them? So this vector is 2, 7. The dotted with this vector is 7, negative 2, 7, negative 2. And that is going to be 14. 2 times 7 is 14, plus 2 times 7 times negative 2 is negative 14, and that is 0. And that is no coincidence. Every time, well, every time you get 0 in the dot product of two vectors, the two vectors have to be perpendicular to one another. Now, this is not the only perpendicular vector. You can have a vector that is going this way. Yeah. Oh, I guess the angle. I think I'm gonna sneeze. Head. Excuse me. So if you go this way, this vector over here is going to be negative 7, 2. And if you take 2, 7 and multiply with negative 7, 2, let's see, we're going to end up with 2 times negative 7, negative 14, plus 7 times 2, positive 14, and they add up to 0. But those are not the only ones. You can have a vector that is way longer. So you could have 2, 7, and how about 14, negative 4? So twice as long. I'm not going to draw it because it's going to get kind of messy, but this vector twice as long will be about there. And so when we find the dot product between those two vectors, 2 times 14, 28, plus 7 times negative 4, negative 28. Sure enough, we get 0. So we can definitely tell that whenever we multiply a vector with another vector and the product, the dot product is equal to 0, the two vectors are perpendicular. So a question we can ask ourselves is, find a perpendicular vector to 1, 3. Okay, that is actually pretty easy. 1, 3. We want another vector, so the dot product is equal to 0. And that second vector will be the answer. The thing is, there's too many choices almost. You can fix one number, say, will 1 work? Will any number work? Let's try 1. So 1 times 1 is 1 plus, now here's the other number. So I picked 1 at random. I just picked a number at random and see if that forces, because there's too many numbers, too many vectors that will answer the question. So I want to just pin down one of the answers by fixing one of the numbers. So, okay, 1 times 1 is 1. Now I need another number so that multiplied with 3 gives us a number, a product, that when added to 1 gives us 0. Well, that product has to be -1. So, I need a number down here, so 3 times that number gives us -1. Oh, the reciprocal, the opposite reciprocal will do 1/3. So this is not as pretty because we have a fraction, but nonetheless, it is a vector. It is a vector. So plus -1, that gives us 0. So here's our vector. So one vector, if somebody asks you to find a perpendicular vector to this one, to 1, 3, this is the way you can start. Now, somebody else could say, wait a minute. So there's the answer. 1, -1/3. Those are the two coordinates. But somebody could think, wait a minute, what if we do 3? So 3 times 1 is 3. And now I need a -3 to get 0. So what number can I use here to get a -3 so that I can have a sum of 0? Well, that's going to be -1. So this is a little prettier because it doesn't have fractions. Not like fractions are ugly. I'm just saying they're not as complicated. I mean, whole numbers are not as complicated, or integers are not as complicated as fractions could be. Okay. So the dot product tells us whether we have a perpendicular or not. If we don't have a 0, that means that the two vectors are not perpendicular, by the way, and that works even in 3 dimensions. So let's do another example, 8. Okay. Find a perpendicular vector to, say, 1, 2, 3. Okay, so one way to do this is to say, okay, 1, 2, 3. The dot product with another vector should give us blank plus blank plus blank, and that should add up to 0. All right, there's going to be very, very many vectors that will do that. Let's say if we put 1 and 1, yep, then this product, when we apply the dot product, is going to be 1 times 1, 1, 2 times 1, 2, so that's 3. So I need something here. So I pick those two numbers at random, and usually you pick something that is relatively easy, such as 1. And then hope that this one is easy. But if it is, and if it's a fraction, that's fine. That's still acceptable. But in this case, I'm lucky because if we put -1, we get -3, and that adds up to 0. So here we have it. 1, 1, -1 is perfectly perpendicular to this vector, totally and completely perpendicular to that one. Now, there is an easier answer, an easier, way easier answer. And here it goes. So if somebody asks you for a perpendicular vector to 1 to 3, you can simply say, how about 0, 0, 0? Because the dot product, 1 times 0 is 0, 2 times 0 is 0, and we add that, and 3 times 0 is 0. So we end up with 0. So voila, this is also perpendicular to this vector. In fact, the 0 vector, which is the vector made up by zeros, is perpendicular to any vector based on this concept that the dot product is equal to 0. But teachers are not as absent-minded as not to know that that's going to be an answer. So, or that could be an answer. So the way we fix that is when we ask the question, oftentimes we say find a non-zero. So oftentimes I'm going to put an asterisk here, and oftentimes we ask for a non-zero vector that is perpendicular. So in that case, even though this is perpendicular, because we're asking for a non-zero vector or non-trivial, sometimes we call it non-trivial, non-trivial, um, but non-zero is the correct word we will use most of the time. So we want to find a non-zero vector that is perpendicular to 1 to 3, then this would not be acceptable. You have to do something like that. And I could have, 25 different answers. I could have as many answers as students. One student could say, well, I'm going to use 1, 1. Another student could say, I'm going to use 1, 0. Another student could say, I'm going to use 0, 1. Another student could say, well, I'm going to use 1 and 0 in different coordinates. There's a bunch of different ways to go about it. And you don't have to use 1 and 0. You could use 3 and 2, whatever. There's many, many ways to obtain solutions. So there's many solutions. Whoa, so the question could be, how do you find them all? All of them. So if we have A and B in general, let's go for that. Okay, so example 9. Find all perpendicular. Boy, I get excited when this kind of question comes up. All perpendicular vectors to 1, 2, 3. Okay, so wow. So let's go for this. So 1, 2, 3, dotted with A, B, and then we don't know. Okay, I mentioned that one student could say, well, I could use 1, 1, or another student could say 1, 0, 2, 2, whatever. But let's fix those two. And then that will force this one to depend on those two. Once those two are pinned down, then this one has to be dependent on those two. All right, so I'm going to call it C anyway, and we want to end up with 0. Okay, so this is my example 9, and we're going to continue. 9, we're going to continue with this example. So again, we have 1, 2, 3. We're going to multiply with A, B, C, and obtain 0. Well, that means that 1A, so just A, plus 2B plus 3C would have to be 0. And that means that C, C would have to be A plus 2B over, well, subtract that fraction over 3. Yep. So if we come up with those two, so if you just come up with random numbers, so 1, 2, 3, we can mass produce now a perpendicular vectors, and that's the question: how can we mass produce them? I'm going to write the answer, the final answer, at the bottom, but this is what we're doing. Just so think of two random numbers, like 5 and I don't know 7. All right. So just pick two random numbers so that not the two of them are 0 at the same time. At least one of them has to be different than 0. Actually, if both were 0, then this formula will give us 0. So even if those two were 0, we're okay. But that would be the trivial case. Anyhow, so 5 and 7 is 12. Oh, no, I have to do twice the second one. So 5 and 14 is 19. So the third number has to be negative 19 over 3. There is one that is perpendicular. Another that is perpendicular to 1, 2, 3. So let me just write down the answer. Say, yeah. Say you pick a random number, -8 and positive. I don't want to pick. Boy, this is when I need students to tell me random numbers. 1. There we go. -8, 1. Can we come up with this third coordinate? And the answer is absolutely yes. -8 plus 2 is -6. Over 3 is -2. Flip it, you get 2. So -8, 1, 2 works. What I don't like about this works, by the way, this is good. What I don't like about this particular formula is that occasionally we're going to end up with fractions because we have to divide by 3, and random numbers, when we add one number plus twice the other number, sometimes will be divisible by 3, such as in this case, and sometimes it will not. Um, so let me write down the answer. So we're still answering the question, what are all the vectors that are perpendicular to this one? So the answer can be written in a couple different ways. We can say, well, a, b, and then negative of a plus 2b over 3 with a, b being any real numbers. That's too long to write. The way we usually write this is by saying, just putting a comma and saying a, b, comma belong to the real numbers. So that's the notation we're going to use instead of this. But so this is one answer, and that will be completely and totally acceptable. The only problem is that it has fractions in it. Notice that in this equation, if we solve for a, we don't end up with fractions. We can just do 2b plus 3c on the other side. So if we fix c and b, so another way to write the answer, or, is to say, well, b and c are fixed, and a is going to be -2b minus 3c, comma, where b and c are any real numbers. So this is the symbol for belongs to. And in this context, we mean they can be any real numbers. And actually, there's a third way, and there's more than 3, but 3 are the basic ones. So, or another way to write the answer is to say, if we solve this equation for b, so we can have a and c being random, and then b would have to be a and 3c, negative a and 3c divided by 2. So that would be another way to write the answer. So there's a couple different ways to come up with all and every one of the perpendicular vectors. There's more to this. It turns out that the dot product is actually related to the angle between the two vectors. More precisely, it is exactly the magnitude of one vector. Oh, these are vectors. We did not quite have a notation for vectors yet. You know what? I'm going to use, if I don't say otherwise, we're going to use v and w and u for vectors. So if I don't say anything, those are vectors, assumed to be vectors. And the first letters of the alphabet, unless we state it otherwise, and unless we clearly state what we mean, they're going to assume to be scalars. Yeah. So v times w, the dot product, is the length of v. Well, this is not the dot product, so I'm just going to put the length of w multiplied times the cosine of the angle between the two vectors. So theta is going to be assumed to be the angle between the two vectors. So if you got v from the origin and w from the origin, this angle, theta, is the one in between them. And it is going to be always not greater than 180 degrees. It is always going to be positive. So theta actually not negative and uh, less than or equal to pi. Yeah, yeah. So this is a fact. You can see proofs of this in books, all different books. Yep, yep. And by the way, the length of this is v minus w, or w minus v, the magnitude or the length of that. Um, so this is the length of this is v minus w, or w minus v. Either one of the two is the length of that. So I'm not giving a direction. We have to think of which direction we want to go if we wanted to give it direction. Anyway, um, okay, now the cosine is always less than or equal to 1. There's a consequence of this equation. Um, yeah, so this is a standard equation. This is just a well-known equation for the dot product. Um, if we put absolute value, so if we impose absolute value on this, then we would have, so impose absolute value. And if you have that, then V dotted with W will be, well, this is always positive anyway, so there's no need to do anything with that. That is positive. And that is cosine of theta. There we go. This could be positive or negative, we don't know. But whatever it is less than 1. So this is less than or equal to V W times 1, because 1 is bigger than or equal to the absolute value of the cosine of theta, no matter what the angle is. The most cosine can be is 1. So we have this new inequality, well, new to us. Now here we have to have the absolute value because this is a scalar. This is not a length. This is not going to be a vector. The dot product of two vectors is not a vector, is a scalar. So we can take the absolute value. And that is definitely less than or equal, based on this inequality, to the length of V times the length of W. This is a well-known inequality, and it is called the Schwarz inequality. This inequality is not as essential. It is widely known, don't take me wrong, but it is not as essential to linear algebra, in my personal opinion. Um, some people will say, wait a minute, this is super duper important. But in my view of the topic of linear algebra, at this point, it's not as essential. Maybe I'll bite my tongue later, but at this point, so that's why I say it is my opinion. Um, you know, and one of the reasons why I'm making emphasis of that is because in the last video and in this video, I have said a couple times, 2 or 3 times, oh, this is very, very important. This is very essential. Well, this one is not as much. It is a little more obscured and yeah. So FYI, and again, that is my opinion only. And we also have the triangle inequality. Let's see. The length of V plus W has to be less than or equal to the sum of the two individually, the two lengths. Yes, this is similar to V minus W. If you just see, if you use negative W here, then you can just say V minus W. But then the magnitude is not going to affect the negative. Yeah. So there is a derivation. And this is due to just a plain fact of geometry. If you have V and W, this length is the magnitude of V minus W. And so let's see. Oh, and this forms a triangle and on the plane, a geometric triangle. So how long can this be? Well, this can be as long as those two put together, but not longer. Yeah. So that's what we're saying here. The third side, which is this one of this triangle, cannot be any longer than those two together. So this angle can open out only to 180 degrees, in which case this would be maximum. And you're saying, well, wait a minute, you have V minus W, and here you have V plus W. Well, that's the way the triangle inequality works. How can I justify this if we have that? Well, simply the magnitude of V minus, label this as negative W, and then this will become negative of the negative. Yeah, and then you'll have it. So it's a matter of perspective, yeah, only. So that is another inequality. Um, it's a good inequality, just like the other one, Schwarz inequality, but in my personal opinion, it is not central to the studying of linear algebra. Again, that is my opinion only. Um, oh, one more thing. I need to make sure we go over one more little thing, and that is unit vectors. Um, unit vectors. They are important. They are more important to calculus than to linear algebra per se. Um, yeah, calculus, multivariable calculus uses unit vectors more extensively than linear algebra, to the best of my recollection. Um, let's see. So 1, 3, let's do an example, and I want to keep up with the numbers. I think the next example is example 10. Yep, example 10. So the vector 1, 3 has a direction, 1, 1, 2, 3. There we go. And the length of this vector is, if you use Pythagoras, this side is 3, this side is 1. So 1 squared plus 3 squared is 10. So the length is square root of 10. Yeah. This vector is too long. So oftentimes we want the vector to be a unit vector, just one. And of course, it cannot even line up with this because that's already going to be too long. So it's got to be a little shorter than lining up with the 1 unit here. So it has to be shorter. How do we obtain the vector exactly in the same direction, but shorter? How short? Well, so it is 1 unit long. What we have to do is simply divide by or multiply by the reciprocal of the length. So uh, 1 over the square root of 10 times 1, 3 is a unit vector. Or 1 over the square root of 10, 3 over the square root of 10 is a unit vector, and it perfectly lines up with the given vector. It is going in the same direction and pointing in the same way, except that we have what I would call pure direction. So this is what I personally call pure direction, because there is no length. By no length, of course, you may think, well, it isn't 0. Yeah, but as a factor, 1 is the unit of multiplication. So as a factor, the length is 1, and that is perfect. That means that there's not a lot, there's not too little. See, 1 is the perfect number for that purpose, because 1 is 100%. See, if you have anything bigger than 1, 1.2 is more than 100%, 120%. Or 0.8, that's going to be 80%. So this is going to modify, the size of this is not 100% is what we want when you have a unit vector. That's when I call it, we have pure direction. However, I think that concept of unit vector, I have to think this more through, but superficially, I think it is used more extensively on um, calculus, because when you do derivatives and derivatives, you want to make sure that your slopes are correct. You're measuring against a unit, not against something that is not 100% a unit, kind of thing. There's one other thing I wanted to show you very quickly, as long as we're talking about directions. Well, um, 1, 3 goes in one direction, and -1, -3 goes in the opposite direction. So what is the dot product of those two? Well, that is -1 plus -9, which is -10. So if the number we obtain is negative, that means that one vector is going in one direction. Well, and the other one is not going in an acute angle. In this case, they're going perfectly opposite. But if you get a negative number, what we mean is that the angle is more than, we have an obtuse angle. In this case, it happens to be 180 degrees because it is perfectly opposite. Um, yeah, so if that product is negative, then angle between vectors is obtuse. Okay, so gee, let's just do a table. Dot product, nature of it, and consequence. Well, angle between. Yeah, that's probably better. So if the dot product, well, it's always a dot product. There's no need to say nature, so ignore this. Is negative. Then the angle between is obtuse. That's what I just set up here. But then I was going to say more, and I didn't want to write more paragraphs, so that's why I'm making it into a table. Obtuse. If positive, then acute. Well, obtuse or 180 degrees, acute or 0 degrees. And as far as the directions go, if you get 0, then you get exactly 90 degrees. Not obtuse, not acute, 90 degrees. So that is a consequence of the dot product. And that's why the dot product is used extensively in physics, because it tells us whether things go in the same direction or they go perpendicular. And so when you're computing work in physics, you need to know how much the direction of the force contributes to the motion of the object. And so you need to know how much they are parallel, those two motions, or not. So that's why, one of the reasons why the dot product is important. All right, I think I covered all the topics I wanted to cover in this second video. So we will stop here.